Okay, so welcome back. Thank you for showing up in the morning session today. Like we discussed last time, we were going to do like 3 topics overall for these 3 sessions, maybe. And last time I talked a lot about lower bounds. And today the plan is to talk a little bit about hardness versus randomness. But because the lower bound, the final proof was kind of very much at the end of the discussion, I said that I'll kind of repeat some parts of it. Yeah. So maybe let's spend some first 15 minutes or so just going over what we did last time towards the end of the session. And then I'll start with hardness versus randomness. Okay. So we were discussing this lower bound proof for sigma pi sigma circuits last time. And what we said was that first you have a circuit of this sort, sigma pi sigma circuit, convert it into a set multilinear circuit without blowing up the size too much. After that, come up with this partition of variables that this hard polynomial relies on, and in turn that polynomial itself is sort of a projection of IMM. Then you analyze the measure for the hard polynomial, and then you analyze the measure for set multilinear sigma pi circuits. Yeah. And most of it was, I guess we rushed through this last part mainly. So what we could do now is just go over this last bit a bit more. Okay? And I feel like conceptually I was able to communicate most of the stuff I wanted to say, but maybe the computations were not so clear. So most of it is more on the computational side, what we are going to repeat now. But maybe it will make some extra connections regarding concepts as well, and feel free to ask questions if something is unclear. So we have to analyze circuits which look like that: sigma pi sigma, set multilinear circuits. And because of subadditivity of the measure, we can basically just try to analyze this, the thing in that blue box. And then we said, okay, we'll divide the work into 2 cases. The first case is when one of the product gates sitting inside this F has large degree. So let's assume, without loss of generality, that all the degrees are descending order. And then the largest one has at least degree d prime, which is square root d by 2. So then I'll just like open up the computation, which I didn't do last time. So I want to analyze mu of f, but by submultiplicativity, it's the same as product of mu's of fj's. And then I want to in turn analyze mu fj, which I'll just upper bound by mu of f1. Why I could do that is because mu, the maximum value mu can take is 1. So let's just assume that for everything else we see no loss at all. The maximum loss just comes, the only loss we get to see comes from f1. And then let's say everything else is just 1. We are still going to be able to recover the bound pretty easily. So we don't need to do the ugly math of bounding it for each one of them. So this is just a simplification step. And then now let's focus on what f1 looks like. It looks like sigma pi sigma, right? And then maybe the sigma has some fan-in. The degree is this d prime, obviously, that's what we assume. And these are LIs. So again, I'm going to do the same thing. Subadditivity will give you S1 here, but S1 can't be more than S, so let's just bound it by S. Then I apply mu and apply it to this object. Submultiplicativity kicks in again, and I just want to analyze the mu for one single Li. And now this is easy. Yeah? Because a single linear form relies only on this one set of variables. And if it just relies on one set of variables, it's as good as having this matrix which is rank 1. Yeah, because it's just like only one row that is active. Everything else is anyway 0. So the mu for this is, the rank of the matrix is 1, divided by square root of number of rows times number of columns. Number of rows is just 1, let's say. So number of columns is whatever is the size of the set on which Li relies. And so you get, so I just did it in one step last time and I spoke a lot about how to do it. But now all the math is on the slides. And it's very simple math, right? Like, I'm not doing anything very non-trivial here. So yeah. All good so far? So then I just expand it out like this, right? Question?
Yeah, can you go back 2 slides?
Yeah.
Can you remind us what, like the measure on L sub I looks like?
Definitely. So, does everyone remember the measure itself? So, for a matrix M obtained from a polynomial f, mu of f, I think I called it like this, is equal to, or we defined it as, rank of this matrix divided by number of rows of this matrix product number of columns of this matrix, right? Yeah, but recall now, if f equals a single Li, that just relies on one set of variables from this partition of variables we were looking at. That's the property of set multilinear circuits. Okay. So if you have linear forms in 2 variables, then when you multiply out, it stops being set multilinear. So it's a property, it's something you can think of offline, that every linear form at the leaves will depend on only one set of variables. Okay? But if that's the case, what is its matrix going to look like? Yeah? Recall that the matrix just has rows labeled by variable sets on which the polynomial depends and column sets. Okay, so this xj could have been a y variable or a z variable. We decided to put y variables on the rows and z variables on the columns. So let's say, without loss of generality, this was a y variable. Then I'm just going to have one row in this matrix, the one that corresponds to this y set of variables. And then here I'll start adding coefficients of whatever this linear form is. So that's all it is. So if it's just like one row, its rank is 1. So the numerator of this, for the mu of Li is basically just, I can even say it's equal to the rank, so rank 1 matrix and xg, whatever this set is. Does that clarify things?
And when we say number of rows, number of columns, that doesn't depend on the x, right? It's just like the...
It does, right? It depends on, so, okay, maybe I misspoke here. It depends on all monomials you can form using variables here. So, but really this is like a rank 1 matrix. Because if you tell me, so just give it a thought, it's not so difficult. Yes? And now it's really only a computation from here on, because all you need to do next is bound these sizes. We know that every set size is at least as much as the size of the smallest set we had in our partition, which was like this. And then you have d prime of them, so you have 2 to the d prime. And then because we are taking square roots, it's like L by 2. This is just pure computation. And then by plugging in the values for L, one can quite easily observe, I mean, this is just a substitution for the value of L. And then noting that, in fact, d prime is at least square root d by 2, which was our assumption to begin with in case 1, we get this one. Okay, so maybe you need like 5 more minutes to process it when I'm not speaking, so please do that after the discussion. But I think it should be quite easy to.
What is K?
K was the size of the large set 2 to the k.
Oh.
Maybe I should have reminded you of that. Yeah. So there were set sizes of 2 kinds: the large sets and the small sets. The large sets were of size 2 to the k, and the small sets were of size 2 to the L, where L was this k minus 1 by k by square root. Okay. Yeah. I would like you to think of this number as something that is not magic. I mean, if there's one thing I want to convey through this computation, it's for you to not think of this number as some magic. It should be a number that comes about for the second case, okay, which is this one. Yeah, this number logically kind of falls out when you want to defeat sort of this case. You want to get low rank for this case, okay? And let's see why. And as I said, conceptually, it's just this idea that rectangles are not squares. This is really what this boils down to. And let me just say it, let me just put a simple puzzle here. So I tell you that you have to pick A, positive numbers, and B, negative numbers. Okay? And you have to do it such that 1 by square root d is a very bad number. So let me just like do it through some simpler example. Yeah, both A, so A plus B shouldn't be more than 10. You can't pick more than 10 numbers in total. Yeah, but also each number, both positive or negative, has to be between the strict range of minus 0.05 and plus 0.05. Okay. You have to pick all the numbers from this range. Can't pick more than 10 of them. I want you to make sure that when you add all these A's and B's, they become an integer. Is that possible? Yeah.
Sorry, A's in that range of, are A being real numbers?
Yeah, real numbers. Sorry?
Depends if 0 is an integer.
Yeah, okay. Let's 0 is not an integer. Sorry. Good one. You just can't do it, right?
No.
So why can't you do it?
If you look at the influence supremum of the set it makes, they're less than 1 and greater than negative 1.
Exactly, right? Like they're so small, like they're so close to 0. It's just not possible that if I take only 10 of them that they can overshoot a number like 1 or 2, reach anywhere close to 1 or minus 1, right? No matter what I try. So it's like saying that if I have some precision and I can pick very few numbers with that precision, then I can't go to the next integer value that just goes beyond this precision. And that's really what is happening in this case too. Notice that your degree of every fj is quite small. It's like these numbers here. Yeah, so you cannot pick too many of them. When you say that degree is small, what it says is that you cannot pick too many of them. Okay? So let's see how this A and B I gave in a simple example maps to this case. We want to analyze the rank for a specific fj, let's say, whose degree is reasonably small. So what can this fj consist of? Or let's say without loss of generality, I'm trying to analyze f1. It can have, say, A many y variables and B many z variables. Think of, A as this positive numbers and B as negative numbers. You have to add them together so that the degree is overall at most square root d by 2. Yeah? But then I know from this exercise we saw in the problem sheet as well that mu of f1 is upper bounded by this number. Yeah? What is this number exactly? If I figure it out correctly, it's going to look like one of these two quantities or min of these quantities. So really what's of interest to me is the value AL minus BK, right? And I want to understand how large can this be. Okay, now it maps to this problem exactly, right? Yeah? The problem is slightly different maybe because you are allowed to pick B many minus ones and A many 1 minus 1 by square root d number. Yeah? So what you are allowed to do in this new puzzle now is you can only pick, you can pick numbers alpha 1, alpha 2, etc. up to alpha a. They should, you know, so A is not under your control. So pick A and B such that you have to pick B many minus ones and A many this weird number, 1 minus 1 by square root. And you have to add them together such that this number actually becomes large. I'm claiming that's just not possible. That's all. That's really all we are trying to say in this whole proof. And that gives you rank deficit. Because if this number became close to 1, okay, then what would happen is you'll get rank to be 2 to the k. But you know, 2 to the k is like the most the rank can be. So we won't get any rank deficit. Yeah? To witness some rank deficit, we want to say that this number can't be very close to 1. Vaguely speaking. And that's all I'm trying to prove now. Yes? Great. And then there is a little bit of math for this. Maybe there are like 2 cases. If A is less than B, then you know both A plus B together form the whole degree. So the minimum has to be less than the average, like less than half of the total. And then in this case, if A is less than B, the number we were interested in is going to become negative up there. Because as it is, A adds positive numbers which are smaller than 1. B is adding minus 1 every time. So if A is less than B, E is going to be negative. And how negative is it going to be? It can be easily bounded by this simple computation. It's just that much. No rocket science in this part at all. In fact, nowhere is there any rocket science. And on the other hand, if A is greater than B, in this case, one needs to observe that this number is substantially far from 0. And actually, one can prove by a little bit of observation that this is bounded away from 0, 1, and so you get a bounded. This is not so difficult, and that finishes the proof. Yeah? Now I need to kind of do submultiplicativity because I bounded one of the FIs, but really F is a product of these FIs. And then by observing that the total degree of the node is D, and you have a square root D sitting below, you know, the product will become sum in the exponent, and you'll get this. All good? Again, I would argue that this is basically now just simple computation, so there's nothing going on there. All right, so that's about the lower bound proof. Yeah. What about larger depths? So in the beginning, when I started telling you about this result, I said not only does this hold for sigma pi sigma, it actually holds for all depths. And in fact, the proof is very similar. You first take the sigma pi to the delta sigma circuit, like large depth circuit, convert it into a set multilinear circuit without blowing up the depth too much and size too much. In fact, we were in our paper able to do this just for characteristic 0, but Mike Forbes came along. I mean, we really tried to make it work over all characteristics for the last 3 years, but we couldn't. And then Mike Forbes came along, and in his paper at CCC, he not just gave 1 proof, but 2 proofs for doing this. So, he proved that it's really, really possible. And then he used this DIMACS identity. He got the best paper award at CCC for this work. And then, once you have this set multilinear, it works over all characteristics, you do the same business again for the lower bound. Yeah. Again, you have sets of small and large sizes. Large size, let's say, just stays the same. I make the adjustment on the smaller side. And the only thing you'll see that has changed here is instead of 1 minus 1 by square root d, it's become 1 minus 1 by square root 2. That's it. Yeah? And it then works out. Again, something similar. So step 3 and 4 remain the same, and step 5, which we just went over right now. Again, the only non-trivial part you need to show here or observe here is that this number is substantially away from 0 again. Yeah? And actually with this, I mean, if you're curious, it will be quite easy to read the proof now. I've basically given you everything you need to understand.
Why does this only apply for char 0?
One more time.
Why does this only apply for characteristic 0?
This one?
Yeah.
No, this works everywhere. The rest of the steps work everywhere.
Multilinear amount is for every
Yeah.
field.
The what we just saw, this whole lower bound proof for depth 3, right? Depth 5 really, set multilinear, that works over all characteristics. The only bottleneck in our whole proof where it didn't work over all characteristics was over there, and now it's been overcome by Forbes' result.
Oh, in the first step.
In the first step. Only in that step that we had this bottleneck, and now by a very clever, 2 different clever arguments, he managed to prove it. Also very nicely written paper. In fact, this DIMACS identity is a lot of fun. You can, I mean, if you're interested in such identities, it's a very nice trick to know. Yeah, so this is the recap for the low bound proof. Yeah. So now we really start our today's session. All good? So this is, we are going to talk about hardness versus randomness. Okay. And the star of the show for this part of the discussion is really a polynomial identity testing problem. Wondering whether the user. Okay, so the problem is that you are given a circuit C, and it's of size S, let's say. It computes a polynomial P of degree D, and now you want to know whether the polynomial is identically 0 or not. That's the question. And note that it's not the same as saying polynomial function being 0. You know, because over F2, let's say, x square minus x just evaluates to 0 all the time. But it's not a 0 polynomial. But you want to check whether the polynomial is actually 0 or not. That's the goal. And the problem is often considered in 2 different models. This is a black box model where you don't get to look at the circuit really, but you only get to ask questions to the circuit. Is the polynomial evaluating to 0 at this point? What does the polynomial evaluate to at this point, etc. So you only get to ask queries to the polynomial. On the other hand, this is the white box model where you ask, you get to look at the circuit, maybe this plus gate is feeding into this multiplication gate, and you decide to use that somehow in your algorithm. Okay. So the 2 models are different. If you're able to design a black box PIT, you can obviously also design the white box PIT because it's only giving you more information. And like you all must have heard at least a few times by now in this workshop alone, but would already know this, is by this randomized test, you can very easily in randomized polynomial time figure out whether this problem, whether the given polynomial is 0 or not. Yeah. But the question people like to ask in this literature is, can you do this deterministically or not? Okay. Right? Some questions? No. And that's of course wide open. For general circuits, we do not know how to do this in polynomial time. This is one of the big open questions, again, that people like to study. And then, oh yeah, we have a non-believer here. Is that the discussion about? Right. Let's see if we can convert him today. Right? Yeah.
For PIT, I assume that it's only polynomials in VP.
Yeah, because we just take this as a part of the input, that the degree is D. So you can work in polynomial time in the input description. And yeah, we'll assume that degree is polynomial. Yeah, actually, I will say degree is polynomial. The polynomial computes a polynomial degree polynomial. The circuit computes a polynomial degree polynomial. Yeah. And the number of variables is n.
Is there any non-trivial algorithm, non-trivial deterministic algorithm?
Yeah, we'll talk about a couple right now. Yeah. In some cases, non-trivial algorithms are known. But in the most general case where you're given just arbitrary algebraic circuit and you want to check whether the polynomial is 0 or not, well, we don't know. Other questions? All good? Yeah. So, here is an obvious definition that pops up. It comes up in the Boolean's case as well. A hitting set for a class of polynomials is such that, it's a set such that for every polynomial, if it's a non-zero polynomial, then there is a witness for it in the set, that there is a point in the set such that the polynomial evaluates to something non-zero in that set. Question?
Is it useful to think of those classes of, like, you take all the polynomials of the same number of variables?
Yes.
And then you consider their ideal, and you take the contrapositive to the variety they define, and then that gives you a hitting set.
So you're saying that, can I just imagine what this hitting set is? You could get a hitting set exactly as you said, but it won't be small necessarily.
No, it won't be small.
Yeah. So what we are interested in is a small hitting set. Yeah, but that is a hitting set. That's correct. Yeah, but it's not an efficient hitting set.
Oh, yeah, sorry, but what I meant is that, sorry, that was not the right question. Are usually those classes of polynomial, when you fix a number of variables, are those ideals usually, or not even?
Well, I mean, if you are saying that they go to 0 or something, I don't know. I wouldn't expect them to be ideals in general.
Okay.
I think, for example, if you're just talking about hitting set for polynomials which have small circuits, all polynomial families which have a small circuit, I don't think they're, I mean, when you say, ideal generated by one polynomial, not necessarily, right?
Not necessarily, because you could easily go out of the class by multiplying it with something.
Oh, okay. Thanks.
I mean, for restricted classes, it's easier to see maybe, but yeah, even in general. Yeah, question.
These things aren't guaranteed to exist, right?
These things are not guaranteed to exist, absolutely. Yeah. Yeah. I mean, existentially, we know that they exist. So, random constructions give you something. Yeah, but a priori, no, you need some argument. By this random, like counting argument or something will give you this. So it has been proved by people that such hitting sets should exist. In fact, the existence for hitting set, the size is quite small. I don't have it on my slides, unfortunately, but it's known. However, explicit Hastings sets, which are small size, we have no idea.
What about like the example you gave for a polynomial that over f2 that isn't 0 but is 0 at all?
Yeah, you want to check its identity over f2, or what are you asking?
I guess I'm asking if that contradicts the existence of these things.
I'm saying if you just wanted to check if x square minus x is the 0 polynomial or not. I mean, just evaluations over f2 aren't going to tell you much.
Not over f2, yeah.
You
want to just look at a larger characteristic and evaluate it there. That's right. I mean, you do it over complexes, it will immediately be clear and be true most of the time that it's not 0, right? Yeah, so you need to choose the right characteristic and evaluate it there. The randomized algorithm would do it, right? So, yeah.
I guess f2 is a weird field because even, I guess I'm jumping ahead, but we'll be connecting this to lower bounds actually, and over f2 like permanent is easy.
Yeah, that's right. So hardness, coming up with hard, but one can come with hard polynomials over f2. It doesn't have to be the permanent. Yeah. Yes.
I guess from what I've seen, like the convention is to use a large enough field.
Yeah. Even for something like this, you would have to assume that the field is at least as much as, I don't know, like degree, some function of polynomial function of the degree and the number of variables or something. So we'll assume that for now. Other question? Yes. So of course the question, as I said, is to design the important question which we would like to understand the complexity of is, can we design small hitting sets for general VP? Okay. Why does one study this question? I think it's a good idea to always ask us this question, right? Like, okay, so one thing that people like to say is this is a very natural and fundamental question. Yeah, so this is of course debatable, but a lot of people do believe this. Then the other thing is that they share connections to circuit lower bounds. So, you know, that could be another reason that some people would like to study it. Okay. Then there are situations where this is of algorithmic importance as well. And I put a star there because I'm going to just give you one example after this slide. And then also, people believe that this also captures like a general de-randomization in the algebraic setting. Like it's a little more general than the way it's stated as a question, PIT. Because you know, a lot of the times, interesting de-randomization questions boil down to checking whether a certain polynomial evaluates to 0 or not. Like it happens more often than you can ascribe to coincidence somehow. So therefore, people also like to believe that maybe it's kind of more general than we think it is. Okay, so now let me tell you one very simple example, algorithmic example where this comes up, PIT comes up. So here is a graph problem. You're given a bipartite graph and you want to check whether it has a perfect matching or not. Okay, very simple problem. I guess everybody has seen it before. A perfect matching in a bipartite graph, I would like to encode it somehow as a polynomial. So what I do is, I first consider the bipartite adjacency matrix of the graph, which is that the vertices on the side in U are the row variables, and the vertices in V are the column variables. And for I comma j, I just put a variable now. Yeah, I don't put 1 if the edge is 1 and 0 if the edge is 0 or something. For now, I just abstract this out as a matrix over variables. Yeah? So it's just a matrix, generic matrix with n square variables. That's what it is. Okay. Now here is a very simple observation that the determinant as a polynomial, yeah, not evaluated at some point or something, just as a formal polynomial, is a 0 polynomial if and only if this graph has no perfect matchings. I think I should say here, No, I have to say over evaluations, right? Because this is a non-zero polynomial no matter what.
There is no?
Yeah, I should maybe say the following, that this matrix is not what I described right now, but if the edge is present in the graph, then I put xij,
Zero.
okay, and 0 otherwise.
Yeah.
Yeah, xij if ij is an edge, sorry I misspoke, and 0 otherwise. Now what I've written is correct. Yeah? Because now every permutation that you sum up in the determinant will become 0 if that permutation is not a full perfect matching in this graph. Yeah? So this polynomial is identically a 0 polynomial if and only if there is no perfect matching in the graph. So the problem of computing perfect matching in bipartite graph, which a priori may not have anything to do with polynomials, reduced to computing zeroness of a polynomial. In fact, we do know randomized parallel algorithms for this problem. Yes?
Oh yeah, so this by itself does not give the actual matching, only tells the existence.
This tells only the existence. It solves the existence problem. People have been able to solve the computation problem, search problem as well for this, in about the same complexity. Yeah, and this was the work, this is very classical stuff from the 80s, randomized algorithm. Yes, sir.
Wait, so you can reduce this problem of finding a perfect match in a bipartite graph to the decision problem of
the PIT problem, yeah.
PIT, but like, does the search version reduce?
Not exactly, it does not exactly reduce.
So, like if I give you a black box, which
Yeah.
will give you test for polynomials true or not, given that like with a polynomial number of black box calls, can I find a perfect match?
Offhand, I don't know how to do that actually. I don't think there is a direct reduction, as far as I know. But I'm definitely not an expert in the area. Maybe somebody knows this. But from what I vaguely remember, I don't think that is known.
Maybe just for like NC algorithm?
Yeah. No, not for general NC, for perfect matchings. For perfect. Yeah, so randomized NC algorithms have been known since the 80s. This work was in the 80s, I believe. And very recently, in 2016 and later, people have been able to de-randomize this algorithm. Okay, so now we actually know quasi-polynomial time deterministic algorithms for this. And it's a big open question to find a polynomial time.
They call it determinant of the NC.
Of the NC, yeah. I mean, otherwise you know
It's
deterministic
polynomial
polynomial time
time,
algorithms for
polynomial
this.
NC.
Yeah.
Yeah, I guess for like the search to decisions, you try that and you get something that's not parallelizable.
Okay.
Yeah, the randomized NC comes from assigning like random values to the xij, I believe.
Precisely. Yeah, it is a PIT actually. You just basically assign random values and check whether it's 0 or not. And then determinant computations is NC. So it's sort of like, it's not so difficult to convince yourself that it's RNC.
Can you describe what quasi-poly means in the NC model?
Yes, so it has depth log or log square, and the size is like n to the log. So that's the size of the circuit. So what it also means is that what they were able to do essentially in this algorithm is that this algorithm uses polynomially many random bits, and they were able to bring down the seed size to something like log square or log, some polylog. And that gave them a quasi-polynomial blow up once you do the standard, go through all the seeds. And so this was really a truly de-randomization result. And an extremely beautiful paper. Like, I highly encourage you to read this paper. It's really beautiful. One of my favorite papers, I would say.
So Svenson Dynasty was it did something more, right?
Yeah, I'm not so sure. I see that everywhere they are mentioned, but I
So
didn't
that-
keep up with the
I think
literature after that.
Sentient anarchy just does general matching.
Okay.
Not just bipartite graph perfect matching.
But
Perfect matching in general graph.
okay.
Then Gurjar-Theroff also did all linear matroid.
Yeah,
problems.
more. Now,
Quasi-
now even matroids are known. The similar problem for matroids is known. But like I said, I'm not an expert on this area. Just thought that it is a very nice application that people should know. Yeah. Fantastic. Okay, here is another interesting problem that people like to study, which is polynomial factorization problem. Okay, what's this problem? You're given a polynomial f, and suppose it's given to you as a circuit. You want to compute, say it's f. It is factorizable. Then output its factors. Yeah. I mean, for this example, for this I just said f1 and f2, but you can ask for all the factors or whatever. Yeah. So another very beautiful result says that if a polynomial has small circuits, then in fact all its factors also have small circuits. Yeah. And this is, I think, a fact worth knowing. So it's not like you have a polynomial and then suddenly factors become very difficult to compute. No, it's not like all polynomials are well behaved in that sense. That if it is tractable in itself, all its factors are also tractable. It shouldn't be. I mean, it's not clear a priori why this should be true. It requires a proof. Okay. And even randomized algorithms are known to compute the factors. So it's not only that it's known that these factors are easy by some sort of existential argument. There are randomized algorithms for this. And one could ask, can I de-randomize polynomial factorization? I mean, this would be super helpful actually, because factorization algorithms are used everywhere in implementations and so on and so forth. If you can de-randomize them, perhaps you get some sort of you don't rely on too many outer objects for that algorithm, and it becomes like more self-contained. For many reasons, people like to do this. Of course, we don't know how to do that, but we can connect this problem to PIT. Okay, so for example, just look at this polynomial over here. Okay, f of x plus yz. Say yz are new variables, two new simple variables. It's very easy to see that f of x is a zero polynomial. F of x is a zero polynomial if and only if f of x plus yz is reducible. Okay. So what it's saying is that factorization reduces to deterministic PID. It took a bit of work to show that deterministic PID can give deterministic factorization as well. Yeah, and it's been done in the work of Špilka and Volkovich, and also Swastik Kropati, who was speaking yesterday, and Shubhangi Saraf and Špilka. So they achieved the other direction as well. Yeah, question.
Why does it have to be deterministic for this to work?
No, it doesn't have to be. But if it is deterministic, then this is deterministic. And if this is deterministic, so is that. So whatever is the so this reduction, just saying that algorithms for this give algorithms for this. Nothing other than that. But in particular, if it's deterministic, then. And the other way around also is known to hold for deterministic. So one can just state it this way.
Okay, so for this direction, that's basically no overhead, right? For this direction, is there like a big overhead?
Yeah.
Okay.
Yeah. Exactly. Yeah, this is just a simple observation. Okay, so factorization also has connections to PIT. And now I'll just tell you the final connection PIT shares, which is also, in my mind, a very important connection, which is to hardness versus randomness. Okay, so we have these three islands here. On the one hand, you have lower bounds for circuits. On the other hand, you have black box PIT. And here you have white box PIT. And because I have hardness versus randomness on the slide, one may immediately start thinking in the Boolean world, but let me remind you that we are talking about algebraic. So these are algebraic circuits that we have lower bounds for. PIT is anyway defined for algebraic, so there I'm not so worried, but these lower bounds I assume are for algebraic circuits. Okay? So we have these separate islands, but they all have connections to each other. Okay? Very related. So one connection is easy to see, let's get that out of the way, which is that black box PIT reduces to white box PIT. If you can solve it in the black box model, which is harder, you can obviously solve it if you have more information about the circuit. What requires some work, and we'll talk about it shortly, is that if you have strong lower bounds, then you can get PIT algorithms, deterministic PIT algorithms in the black box model. And if you have deterministic PIT algorithms in the black box model, then you can get circuit lower bounds. Okay, so it's like a tight connection between the two. And how tight, we'll talk about it. We'll work out all the parameters. So the idea is, I'm going to tell you the proof of both of these. Okay? And then the final connection, which was also established in the same paper by Kavanaugh and Pagliazzo, is that even from white box PIT, you can go to lower bounds. So now this island is like fully connected. All three islands are fully connected to each other. Okay, and I put a star here, not because I'm going to talk about it later, I'm not. But this is like a green star here, which is to say that it comes like star-stars condition applied kind of star. So it doesn't just give algebraic lower bounds, it kind of has two consequences, either this or that. So one of them is algebraic lower bounds, the other is a Boolean lower bound. So permanent, either permanent is hard or NX is not in B/1. So this is this direction I think many people who know hardness versus randomness in the Boolean setting are more familiar with. What people may not have seen are those two, and that's the one I'm going to talk about. Yes.
Either permanent is hard or
NX is in NX is not in P/poly.
in this algebraic model?
No, okay, so that's what. So white box PIT, which is an algebraic problem, de-randomizing that has connections to not just algebraic, like it shares connections to two worlds in some sense. And we don't know which one is true. It says that if you can do PIT, de-randomized PIT in the white box model, one of the two must be true. One, permanent is not easy to compute, which is also a hardness result, or NX does not have small polynomial size circuits, which is like a Boolean impossibility result.
I guess both of them imply NX is not in like VP, maybe?
Yeah, in VP.
VP/poly.
Yeah, exactly, yeah. It can be stated in what DJ is saying is that it can be stated in completely algebraic way also. It's true. Yes. So are the results clear? And we are going to prove now each one. So first, let me tell you why black box PIT gives lower bounds. That's the easier side of things. You know, this lower okay. Suppose there are deterministic polynomial time black box PIT algorithms for a class of circuits C. Then what does it mean? It has a hitting set. Right? There is a polynomial size hitting set such that every non-zero polynomial from this class has a witness in this set, witnessing that it's non-zero. So existence of efficient algorithms mean that such hitting sets must exist. So now comes the interesting part. You have this polynomial size hitting set, come up with a polynomial that's a non-zero polynomial, but it vanishes on this entire set. You can quite easily come up with such polynomials. Their degrees and their number of variables, etc., will be all tractable because the set itself has small size. But then, clearly, this polynomial is not in this class of circuits. Question?
Should we be convinced that polytime algorithm implies small hitting set?
Yeah.
Okay.
Yeah. That's because basically in the black box setting. In the black box setting, all you can do is like have a set of queries to this. Yeah. It's not at all clear why this should work in the white box case, but for the black box, it's kind of, that's the definition. But then this polynomial is not in it. Again, very simple proof. Here is an interesting conjecture that I found when I was preparing for this part, and I had never seen this conjecture before. But I found it very interesting. It's a conjecture. I don't know when this was made, and I don't know how to find it. But it is in the slides presented by Amir Shpilka, who spoke about algebraic complexity. Like he gave a crash course at EPFL, or I want to say ETH, somewhere in Switzerland. He gave this crash course in 2020. And in his slides, I found this conjecture. So, and he ascribes it to Manindra Agrawal, but I don't know exactly when this conjecture was made. So, if somebody knows, I would like to put like a year over there, but I don't know how to do that right now. But what it says is that this is a hitting set. So, it's a bold conjecture. It's a polynomial size hitting set. And he wants you to prove that this is a valid hitting set for polynomials in VP. So, yeah. Question?
I've only seen that used to like show that's a hitting set for sparse polynomials.
Yeah. Something very similar works for sparse polynomials. Yeah, that's good. But this is, the claim here is that this is a general hitting set.
What is R?
R is some parameter bounded by polynomial in the size of the circuit. Anyway, I'll share the slides with you, so you will also have access to this. But if somebody can put a year over there, I'll be happy to do that. Okay, so we just did the first direction, black box PIT to low bounds. Now I want to show that low bounds imply black box PIT. Okay.
So the proof. Suppose suppose circuit class C was formulas.
Mm-hmm.
And you, okay, no, maybe I want ABP. So now I was trying to see, this tells you that PX is not in C, but is it saying that it is in something, it is in some larger class?
So at this point, if I did this very naively, I could just land up with a polynomial in VNP or something. And it's not clear to me that it should be a tractable polynomial by any means. Because in my head it's going to be like product of linear forms, and they could have exponentially many monomials, their coefficients can be quite strange.
I mean, if you're just trying to interpolate a polynomial through polynomially many points, it's a linear system.
You'll have large degrees. You'll easily get very large degrees. Yeah.
So the black box thing, are the queries non-adaptive?
They are what I always forget which one is adaptive.
So
So
I see the answer.
you
and
can
then
even have it adaptive.
Then the hitting set is a bit unclear. Like I look at the answer and then decide.
So there is, I think, you're right.
Yeah, the hitting set can't be adaptive.
Yeah, hitting set can't be adaptive. I want to say that you can actually just make adaptive to, like, there may be like a efficient conversion. Let me just think. Yeah. Question?
I mean, like, while you're, I guess if you're testing a hitting set, like, whenever you find a non-zero point, you're going to halt. So like, all your previous queries are zero.
Yeah.
Yeah,
So
so
there is a conversion. That's right. So this says that there is a conversion from non-adaptive to adaptive to non-adaptive.
So what I guess I'm just trying to repeat what he said.
Yeah.
What are you trying to do in PIT, right? You want to find some point where your polynomial evaluates to non-zero.
Correct.
Well, if it's evaluating to 0, what adaptation are you going to use from it? You just have to do something, sample under point or whatever.
Exactly.
But if you get something non-zero, you're done already. So
Hmm.
adaptive doesn't make any sense.
Yeah. That's good.
So why does P not in C apply to lower bound?
Basically, when you prove a lower bound, what do you want to say? You want to find a polynomial that's not computable by this class of circuits. So say the class of circuits is polynomial size circuits. Right? So now here is a polynomial that is not computable by polynomial size circuits. So that's it. There you have it, right? Other questions? Okay. So what we just saw, and this is very straightforward, I would say. Just say that hitting set gives you polynomial, hard polynomials. That's like a one-line summary of what's going on here. So then the other direction, which in my view is kind of interesting. So let's look at that. So I think something got erased very clearly, but suppose we have a polynomial that's hard to compute. So it requires exponential size circuits, let's say. Okay. So now we want to solve PIT for, say, polynomial size circuits. So I have this hard function, like just fall back to your intuition in the Boolean case, you have a hard function, you want to prove some de-randomization is possible. Right? So it's exactly the same setup. You have a hard polynomial, hard to compute polynomial, you want to solve the de-randomization for PIT. So here is a very simple trick which will not work, but is still useful to know. Okay? And that really encapsulates the proof idea. So suppose you have this circuit C which is non-zero. Okay? Somehow somebody came and told you that if you replace the last variable in this circuit with this polynomial, yeah, it suddenly starts to become 0. Okay? If we know this implication, then it immediately implies that this should be a factor, because when substituted, I get a 0. But that also means, from the Kaltofen's result we already discussed, that if a circuit is easy, all its factors are also easy. As a result, if this is a factor, it should have a small circuit. Yeah? But that's just not possible from our assumption. Yeah? So if we are able to make this proof idea work, we are in business, basically. Okay. What we need for this idea to work is a Nissan-Wigderson generator and a hybrid argument. Okay. So let's take a 5-minute break and we'll get to that. Yeah, question?
Why doesn't this work as is?
Why doesn't this work as is? Because we don't know this implication, right? You may substitute xn equal to g, but who's guaranteed now that the thing has become 0? We don't know that.
G's image could just be everything, right? Like the
Yeah.
image of G. Usually it should be everything, right?
It is, yeah. It's a hard polynomial. Is that why you're saying?
Yeah, like
Yeah.
usually the image should be everything, and you are not like getting a zero polynomial.
Yeah. In general, you may not get a 0 polynomial.
Is the idea kind of like fix G and then we need to show there exists some C prime that satisfies this?
Well, that's not enough as well, because G is a hard polynomial that we know is hard. Maybe some other variant of it is not even hard. Also, we can't have any scope of choosing what that C is. C is the one I need to do efficiently PIT for. That's given to me by as an input. Yeah. So the setup is, somebody has told me that, look, this is a very hard to compute polynomial, okay, use it as you like. And then the problem that I'm required to solve is check whether the circuit evaluates to 0 or not. So, you know, the problem is still the same, but yeah, you know.
So I'm really wondering about the y variables.
Yeah.
So how could are they fresh variables?
Let's say for now they are fresh variables.
But how could the polynomial with x's and fresh variables be a factor of c, which only has the x variables?
So assuming
Or
that,
they always disappear,
I mean, you could don't think of them as necessarily fresh variables. They could reuse the original variables, but I want to just say that the polynomial could be defined in any kind of variables. Maybe when I instantiating it, it is being done in a specific x1 to xn variables or something. Yeah. Otherwise, it's not clear why.
Maybe I'm missing something obvious, but why do we need the Nissan?
Why do we need the?
Nissan filters?
Yeah, we'll see that. It's not immediately clear. Yeah. But it's basically you want to do some sort of a hybrid argument where you force, after enough substitutions, that the circuit becomes 0 and extract contradiction. So it's kind of this hybrid argument where it happens in the Boolean case as well, you know, like you force like a predicate to become easy somehow suddenly, and then that, very vaguely speaking. Yeah. We'll see it like when. Yeah. So let's take a 5-minute break. Interesting when I'm trying to take a break and the audience is not.
It's too interesting.
So what I'm going to do next is just tell you how lower bounds give black box PIT using this Nissan-Wigderson design idea. So Nissan-Wigderson design, if you've not seen it before, it's a set of sets, each of some specific size. But the great thing about them is that no two of them intersect at too many points. So the sizes of the sets are going to look like some constant times log n, and the intersection sizes are going to be log n. Yeah? And then Nissan-Wigderson design can be used for a Nissan-Wigderson algebraic generator in a very, very simple way. The generator takes t variables from the base set of universe of size t, and then it outputs this n-bit vector. It outputs n polynomials, sorry, which is basically the hard polynomial applied to y restricted to the set of size n. We have n such sets, so you get n polynomials. G is the hard polynomial, and we denote it like this. So for a circuit C, you can simply just obtain the generator like this. This should just remind you of the Boolean case very directly. All good? Now let's see how this is going to help us for doing PIT efficiently. Okay. So for the hardness case, let's assume that the hard polynomial G1 to Gm is on is like 2 to the poly m hard. Okay, so let's say that it cannot be computed by 2 to the m square size circuits or something. M square or m cube, just take the right constant up there. Okay. So now the claim is that the claim we actually wanted to make on the previous slide but kind of failed. That the circuit evaluates to 0 if and only if when the generator applied to the circuit evaluates to 0. Okay? So one direction is of course easy. If the circuit is 0, then no matter what polynomials you substitute and so on, it's still going to be 0. That's not so difficult. But now we need to prove the other direction.
This should be G composed C on some y1 to ym or something, right?
G composed on, no, the polynomial. So let's look at what the definition of G was.
Yeah, that's C composed on.
No, I just denote it like this, right? This is the notation I'm using. This means this.
No, so I meant, so there's two things now. There's P and there's
Yeah.
N, right?
Yeah.
N.
Yeah, it takes a map of T. I know what you mean. Yeah.
So the Y variables
Yeah,
are
it should be like, there should be like a Y here. You're right.
So in the next slide as well,
Yeah, you're right.
the new instance is now on these.
Yeah, just assume that this has that Y.
Y
Okay,
variables.
yeah. Sorry about the typo. Yeah, what this is, so this generator comes with this hard polynomial G, which has its Y variables, okay? So when I apply the generator here, it basically takes x1, replaces it with Y restricted to S1 variables, takes x2, replaces it with Y restricted to S2 variables, and so on, and then applies the circuit C to it. That's what this map is. Okay? And if the circuit itself is computing a zero polynomial, then the circuit, when evaluated at some restrictions of y, etc., is still a zero polynomial. It doesn't matter. On the other hand, we want to claim that if this generator object applied to the circuit evaluates to 0, then in fact the circuit itself should have been the zero polynomial. Okay? So, assume for the sake of contradiction that in fact the generator is evaluating to 0, but the circuit is non-zero. Okay? What does this mean? Imagine that I'm not applying this generator map all at once, but kind of doing it step by step. Okay? This is the hybrid argument that we talk about. So, if we kind of start applying this generator one coordinate at a time, then there must be a coordinate where, till which point the generator is evaluating to 0, but just one before that it was not. Yeah? So keep on substituting these things till it suddenly starts becoming 0. Yes? Okay, so now let's draw a few pictures. The same thing I wrote down there in pictures. The polynomial was non-zero till this variable xi was around, and when I substituted xi with this new thing, it suddenly became 0. Yeah, how could this have happened? Okay, because this is non-zero, there exists some assignment to the variables x1 to xi minus 1 such that this continues to be non-zero. There has to be. So now by substituting those a1 to ai minus 1, this is non-zero, but this is 0. Okay. Let's also assume without loss of generality that the set Si that I finally substituted is on the first m variables. Yeah, I'm just relabeling the variables so that happens. Then we can also see that there exists substitutions for ym plus 1 to yt such that they now still make all these substitutions continue to, they still allow under all these substitutions this to be 0, non-zero, and this to be 0. Okay. What is happening inside this picture? Let me just say it more clearly. We obtained this picture first by substituting these guys and maintaining the zeroness and non-zeroness. Now, what we want to do is we want to kill all the variables that are not in the set Si. Yeah? The only variable that should remain from this point on are y1 to ym, which are the variables in Si. In order to do that, I don't want to arbitrarily kill the rest of the variables. I want to kill the rest of the variables by maintaining the non-zeroness and zeroness of the corresponding circuits. Okay? And I claim that there exists assignments to the rest of the variables that can maintain this non-zero property. Yeah? So just use those guys as your substitutions for rest of the variables. Once I substitute rest of the variables in this fashion, what happens to each of these circuits here? Yeah? They are only on the variables that were shared between the set Sn and Si now, because those Si are the only variables that are alive anymore. So, this polynomial, which used to be y restricted to Sn, gets further restricted to variables in Si, and so on for all of them. On this side too, the same logic applies. Of course, this set was kept alive completely, so it has these variables. Question?
I think I missed something, but why do we know that there's this one that evaluates to 0?
That's the assumption that we started out with. That this is non-zero, whereas that is zero. That was the assumption. We are trying to just propagate the assumption till the point where we reach a contradiction. Okay. So you have this property maintained. But notice now, because of the Nisan-Wigderson design, the intersections of any two sets with any other set with Si is of cardinality only log n, which then means that all of these circuits, which were very difficult circuits to begin with, yeah, are now circuits only on log n variables. So you can just brute force them. Yeah? They were very hard functions. G itself was a very hard polynomial. But now all its variables have been restricted to something that maintains the non-zeroness of the whole thing. But now the circuits are all tiny. Okay? Just brute force and substitute. So now pictorically what has happened is we maintain the non-zeroness and zeroness properties. This has this one extra dangling variable. There I substituted G. But what now? This goes back to our original case where Xi, when substituted with G1 to Gm, G of Y1 to Ym, becomes 0. Yeah? By exactly the same logic now, G1 to Gm is a factor of, or rather Xi minus G1 to Gm is a factor of the polynomial. And that's a contradiction. Simple as that. Question?
Can you go back to the slide that has the proof idea?
Yeah, but maybe some people are still digesting this, so one more minute and I'll go back.
I thought you assumed G requires size 2 to the polylog.
Yeah.
Now you have like poly, so.
That's a contradiction, right?
Yes, but why did you assume 2 to the polylog before?
Yeah, because I think I needed to be more than poly and for every constant. I think these parameters can be improved. I mean, I'm not presenting the proof which is the best parameter known. Yeah, that's a good point. I'm just giving like the vanilla proof and yeah. All good? So I'll go back to that proof idea slide. One goes through these very quickly, huh? Far away. Yeah, there it is.
So we're trying to show lower bounds imply that we can do black box PIT.
Yes.
So
Exactly. So what we said was that if black box PIT Yeah, sorry, I see a hand being raised. Yes. Yeah.
I guess the final idea is that G composed with C is a much smaller number of variables than C.
Precisely.
So I guess just like, what's the contradiction? Like, what's the thing that this contradiction implies?
Right. So what were we trying to do? I think maybe you need this slide. This slide. The zeroness of the original polynomial continues to hold under this. So now, you know, if I was able to prove this, then now just do PIT here. So if I'm able to prove this statement, which is what I did through these contradictions, then it means just do PIT for this circuit.
I think you're asking what was the contradiction at the end of this proof?
Yeah, I'm asking how does this imply BIT?
So, I mean, I guess now, yeah, that was the now there are way less number of variables. So you can just go over all possible assignments.
Yeah, so we use Nissan-Wigderson design in two ways. One was to say that the set sizes are small, yeah, which was helpful for us if you recall here, because the set sizes became small. Each of these GIs we could brute force and just make a small circuit out of, yeah. But then finally, thanks to this claim, we are going to use it another time. Another time, and how? Because we are going to say that recall this is a map from t variables to n, right? And t is very small. Yeah. In fact, t you can make like 10,000 log n or something. Yeah. But for my proof, I was just assuming the very vanilla Nissan-Wigderson where t is like log square. Yeah. But in any case, t is very small. And as soon as you have to do PIT on very small number of variables, then again you can do some brute force C stuff. Yeah, I should have spelled that. Yeah. So now is the whole structure clear?
So hard circuits implies this structure where you can turn the black box PIT problem into a smaller black box.
Correct. That's what this stretch does, right? The generator has a stretch. So your final number of variables is n, but you're really able to stretch it from t, which is very, very small. And then that's the standard, you know, like the randomization algorithm, just brute force kind of. So that's what is happening.
And the hard polynomial is used in the generator.
Hard polynomials, yeah. So generators constructed using the hard polynomial. Exactly.
I don't know, maybe it's connected to what Lee was asking. So in the end,
the size PIT.
So we took the brute force circuits for those instances on log n many variables.
Precisely.
But there we also, because it's log n variables, and we said, okay, G is a hard polynomial which requires 2 to the m. I mean, we said input cube
right.
size or something, but then that will only give us. I mean, that won't give us a poly.
So I'm not going to go through the parameters right now. I think it will require some working out. Let's not worry about it. I think the main idea I want to convey here is that so using the hard polynomial, we've been able to de-randomize PIT. Yeah. What I've done here will give you some sort of blow-ups, and then you can do slightly clever things and get better blow-ups, and a lot of work has been done. I'm going to speak a bit about that as well. Yeah, but that's kind of the overall idea. What I want from here, for you to take back from here, is this overall idea. And then if you find it interesting, of course, go crazy. Yeah.
Do you mind going to a slide right after the post?
Yes, of course. Is it
the next one, the one with all the text?
With all the text, yes. This one?
Yeah.
Yeah. All good? Very good. Yeah, so very simple application of this hardness versus randomness framework, but in the algebraic setting. So this is something, if you have not seen before, it's quite interesting to note. All right. Yeah.
Go back one more slide.
Oh, sorry.
This is polynomial depth.
Good question, right? So you're asking about what is the depth of this circuit. So actually, if we can assume that there is a hard polynomial of small depth, it seems to be that the depth will not blow up so much. Yeah? So then it will be whatever is the depth of the hard polynomial.
It depends on the algorithm of student factorization.
Very good, right? So, exactly. So, we are going to show that on the next slide soon. But, while these circuits do not increase in size and they continue to have the same depth, there is another place where the depth issue will come and hurt us in that. We said that if a polynomial is easy to compute, then all its factors are. But the notion of easiness there was circuits. Yeah? If you now say that polynomial is easy to compute and has constant depth circuits, does now its factor have constant depth circuits? Why should it? We don't know. Right? So one has to be careful. And I'm going to talk about that next. But is this clear? Like this was the main message I want you to get across in this lecture, which is like hardness versus randomness in the algebraic setting. And I hope like that was clear to most of you.
Okay, so this one is
Sure.
making sure I understood what he said. Here the proof, the final contradiction used the fact that factors of easy circuits are easy.
Yes.
And G was a hard polynomial for easy circuits. But suppose you wanted to do this for constant depth circuits, and G was something that was hard for constant depth circuits, then this factorization algorithm which gives you a circuit, we don't know if this is constant depth. It could be large depth and could be easily computing G.
Exactly. Yeah. It could be like depth poly, but size also poly. So that won't give you any contradiction. That will be a problem. Okay. In fact, there are other places where this could be tightened. I was talking about it with Lee in the break also, that when you have exponential lower bound, as far as I understand the parameters, and maybe somebody can correct me here, but from what I understand, if you have exponential lower bounds here, the best you can get are quasi-polynomial PID algorithms, deterministic. And if you have super polynomial lower bounds over here, then the best you can get are sub-exponential algorithms. Okay? These are the connections we know. So now I'd like to first tell you a bit about what are the results known without this hardness versus randomness. Because eventually we want to do PID in polynomial time. And if I were to use hardness versus randomness, neither of them give me polynomial time. Yeah? So let's see where can we do better. And there are a few results where you don't need to spend all that time. For sparse circuit, which are just sum of products, you can do it in polynomial time. And that itself you can see, look at the number of people I've listed. It requires a lot of work to do it for this simple model in polynomial time. Then we talked about this sigma, power sigma circuits. And for that, you know slightly better than n to the log n running time, which is n to the log n running time.
I mean, for the first one, even if there's are these are monomials?
No, in the black box case, you have to still figure out.
In the black box.
In the black box case, yeah. In the white box case, it's trivial. In the black box case, you have to, again, do some clever work here, actually. So that's like the sparse polynomial setting. And there, that conjecture I mentioned by Agrawal, something similar works. That's the hitting set. Then this was done reasonably recently, I would like to say like last decade. And then for this other special class of circuits where you have the top Fanon bounded by k. Yeah? You have only k many products of linear forms. There they were able to get n to the order k running time, which for constant k is polynomial. Or sub-logarithmic k, it's better than what you would get by hardness versus randomness. And then for this model of computation, which I don't plan to talk about, but I just decided to put this stuff on the slide so that you have it to have a way to look at it if you want. There's some interesting algorithms here. Especially, again, I would like you to point to, I would like to point you to this one, which creates like a very nice univariate polynomial, which becomes a hitting set or the, yeah. So it's very beautiful construction again, this one. So I just decided to put these there so that later on, if you look at the slides, you have something to fall back on. But I don't plan to talk about it. Okay. So now let's see what we get from the hardness versus randomness setting. So hardness versus randomness for constant depth. Can we do it? Yeah. Like we had this little discussion over here. What happens to depth? We know already that. So actually by works after Cabanets and Pagliazzo, by bypassing this Kaltofen-like idea, 2 papers were able to achieve this for constant depths. Okay? So the important thing to note here is, I wanted to say the other point first, that Kaltofen's argument does not seem to hold for constant depth circuits, or at least we do not know how to make it work for constant depth circuits. Okay? However, what they were able to say was that Kaltofen does this whole factorization, whereas they say that you don't need to find all you don't need to do the factorization exactly the way Kaltofen does. And they have a better way of doing it which respects depth. Okay, so these were nice pieces of work that this was, I think, early 2010, something like this, and this is very recent, 2019 or something like this. Those names are fully written up there and then abbreviated here below. Right. But now remember we saw this lower bound for constant depth circuit. So by putting together their setup that takes you from constant depth circuits to lower bound, from lower bounds to PIT, we just get PIT, deterministic PIT. Of course, as I said, the time is not polynomial, it's sub-exponential because we only have super polynomial lower bounds. So any improvement in this will give improvements to PIT and things like that. Yeah. So this was the main hardness versus randomness I wanted to say. Couple of questions come out of this regarding factorization which are very interesting. One, can factorization of Kaltofen be done for other models of computation? Like, this whole setup is sensitive to Kaltofen, but suppose tomorrow somebody is able to prove formula lower bounds. Can I lift them to give formula PIT? Deterministic PIT. So even this arrow is not known at this point. So we are far from proving formula lower bounds perhaps, but even this connection, if somebody was able to prove tomorrow such a lower bound, we won't be able to leverage that to get PIT algorithms as things stand today. What about factorization for branching programs? And we talked about the branching program model. There actually we know. And I should have mentioned the references. I don't know how I didn't. This is Thirov and Sinha Babu who proved this. For constant depth, well, yes and no. I would say that this result could be viewed a little bit like factorization result. So the previous one that I told you about, which achieves this connection by Chau Kumar and Solomon and Dvishpil Kayodya. But really for most situations it's open. So can we do factorization efficiently for constant depth circuits, general constant depth circuits? It's not clear.
I mean, you say small degree, like how small? Like polylog?
One more time?
I mean, for small degree, like how small? Like polylog or something?
Yeah, log. Log by log.
Log by log.
Okay, so I actually have done with what I really wanted to tell you. And now maybe in the rest of the time I'll do some. Yeah. Question.
There was a slide, I think pretty early, I think that was like this depth delta
Yeah.
or something.
Yeah.
How does that relate to
Good question. So you're asking how, was it like this one, sigma pi to the delta sigma, something like this, or no?
Yeah, whatever you had in the slide that was kind of like
You'll have to really tell me which one, because I had a lot of slides.
something like that equals something like that with a 2, and it's
The segment linear
Yeah.
converges.
Ah.
yeah. But I guess the question here is like,
Yeah.
Does this mean that we have hard polynomials for like?
Constant depth circuits.
Okay, so delta is like a constant.
Yeah.
Okay.
That's right. In fact, that proof that does for constant kind of works up to log d. So the proof we went over, right, with this sets A, B and different set sizes and so on, that proof I just presented it for depth 3. It can be generalized for arbitrary depth, constant, but it also, like, if you just set up the parameters right and observe carefully, it works up to depth log d. But beyond that, we don't have lower bounds now. So I was really like thinking about what is this extra stuff I want to tell you. And then I decided to, I could have told you like lots of open problems or something, but this is not probably the place for it, because you really want to learn something here, right? Like open problems, yeah, they are open, right? So finally I decided I'll just tell you something I really like. Okay, and I think at least I will enjoy it. So, right. So let's go back to some fun algebraic stuff. Yeah, how algebraic stuff is slightly different from the Boolean case, and then how it allows us to do some fun stuff. So one such fun trick we already saw, which is that elementary symmetric polynomials have algebraic circuit of size n square. We did this by interpolation, or Benot trick as we called it. Yeah. Now I'll tell you a little bit about computing a permanent in a slightly better way. And this is a very fundamental problem, because permanent is like perfect matchings and so on and so forth. So here is a permanent, the definition of the permanent, and here is a formula for it. Okay, this is called the Riser's formula. And if you observe, what is it doing? Look at the i's are the rows, j's are the columns. So it takes like a subset, maybe of size 5. For that size 5 subset, it indexes some of the columns, and it just adds things from that together, only those over here, multiplies things out, and then adds it to the original polynomial. I'm just speaking out loud whatever is written there. So if you understand what's written there, you don't need to listen to me. So, okay, this is a Riser's formula. What does it tell us? Yeah, it's like an inclusion-exclusion kind of formula. Yeah, so if you've seen inclusion-exclusion proofs, they look a lot like this, right? You take a subset maybe of the whole thing, then all subsets of size n-1 with the opposite sign, and then do something with it, and so on. So this really, like, if you just apply inclusion-exclusion ideas and try to compute the permanent, you'll get this. So just to exemplify, just to illustrate with an example, you have this 2 by 2 matrix, then for size 1 sets I get these 2 terms, and for size 2 sets I get this 1 term, and then when things cancel out, you get the permanent correctly, and you can convince yourself offline that this formula actually works. Yeah. And this is like, I consider this like a very trick kind of thing, like magic. It's something you have to play with it for a bit, and then suddenly it pops out. In particular, it shows that the permanents have circuits of size 2 to the order n. Right? A priori, there is no reason to believe why permanent should have circuits of size smaller than n factorial, which we can always write by brute force. But this tells you that in fact it saves humongously on n factorial, by giving still pretty big size formula, but of the order substantially smaller than n factorial. In fact, no such better formula is known for the determinant if you were to write down a formula for the determinant using depth 3. We do not know a 2 to the order n size formula for the determinant. Determinant in our head is an easy to compute polynomial, but at depth 3 you lose this sort of correspondence. Or at least we do not know how to put it in 2 to the order n depth 3 formulas. But for the permanent we have this beautiful risers formula. In fact, now I'll also give you an answer to one of the questions from the problem set. Okay? I'm going to show in one line using the risers formula that permanent is hard for VNP. I told you to compute this in the problem set. I think there was this f of y polynomial which you have to design such that it becomes 1 if and only if it's a permutation matrix. And if you were able to do that, then from the slides of lecture 1, you will be able to show VNP, permanent is in VNP. Here is another way to show that the permanent is in VNP by just using the risers formula. Consider a subset and write it down as a characteristic vector, as we often do. And then you can essentially encode this as such. What's going on there is that you have this y vector and it only takes 0, 1 values. So sometimes this first term is -1 and sometimes it's +1. I adjust it so that it becomes -1 when the set size is odd and even otherwise. And then this is nothing but really like this opened up with a y variable added in there to select the right. So that's like the characteristic vector selecting the right variables and everything else becoming 0. Yeah. So this is another proof to show that permanent is in VNP. Yeah. It's exactly the definition of VNP polynomial. It's summed over 0, 1 valued y variables and something that is computable by small circuits. So there you have it. Okay. But yeah, it's a gift that keeps giving, this risers formula. Let's apply this risers formula to this matrix. It's a special matrix where every row is identical to the other. The first row is equal to the second row is equal to the last row. There are only r variables. It's an r cross r matrix. Every variable repeats r times in its column. Recall the permanent is basically this in general, but when evaluated for this specific matrix, suddenly the x variables have become y variables for some reason in my slides. So sorry about that. Think of this as y variables, okay? You see that basically the permanent of this matrix is nothing but the monomial y1 to yr summed up r factorial many times. That's really what this is, yeah, because no matter which permutation you take, you get exactly the same monomial. But on the right hand side, if I substitute correctly, I get things like this. Okay. This is an indication of something, a phenomenon which is very useful. It says that a monomial can actually be expressed as sums of powers of linear forms. Yeah. Now, if you look at the left hand side, this is any generic monomial, right? Nothing special about it coming from this matrix or anything like that. Yeah? And it says that, in fact, this monomial can be computed as sums of powers of linear forms. Yeah? It's algebra magic, basically. Yeah? So risers formula not only told us that permanent is more efficiently computable than we first thought, it also told us that permanent is in VNP, and additionally it allowed us to understand the monomial complexity, sigma power sigma complexity, I should say, is upper bounded by 2 to the n. And we already saw by the partial derivative method that this is lower bounded by 2 to the n by square root n or something. You may not remember this was in the last lecture, but we did that. Okay. So very interesting stuff coming purely from Reiser's formula. Okay.
So refer characteristic.
Yeah, your characteristic is important because you have this r factorial dangling around. Yeah. To get the monomial, really you have to divide this whole thing by r factorial. And this division by r factorial then tells us that this trick cannot work in any characteristic that's less than r. So you need characteristics strictly more than r.
Oh, so we don't know this upper bound for.
Not as far as I know. Yes?
Yes, I'm thinking, does this like, I guess this wouldn't hold for some like approximation thing that is divided by a big.
So you have to say what you mean by approximation here.
I guess like, I don't know. I'll think about it.
Maybe we can talk about it later. Final trick for today. Okay, beautiful trick. Okay, what is this doing? I claim that there exist univariate polynomials, fi, fj, quite a few of them, s times b plus one of them specifically, or slightly more than that even, such that if you give me sum of powers, sorry?
Power of sum.
Power of sums, good, thank you. I'm like getting hungry now. The power of sums, then it can be expressed as sum of products of univariates. Okay? It's just a trick for now. Yeah? The statement is, I hope, clear. The proof comes from some sort of approximate series idea. Okay? We know that E of x can be approximated by this power series. Let's truncate it at b. And let's call this the polynomial tb of x, the one truncated. Okay. Now let's just observe x to the b. Okay. I claim that x to the b can be thought of as, so I'm going to just have this at the back of my mind, right? And I want actually to compute something like this, power of x1 to xs. So what I'll do is, I'll kind of zoom into this, and instead of computing this with x, I'll compute it with z1 to zs times t. Yeah? So let's expand out e to the power z1, z2 summation of zi's times t. If I look at the coefficient of t to the power b inside this expansion, it's just this guy. Question?
Is this another trick that only works in characteristic 0?
Yes. I'm just giving you like a whole bunch of tricks that work, and if anybody can make them work in other characteristics, it's interesting. For many reasons, it's very interesting. So that's why it's good to know these tricks, so that when you're traveling on the metro or something, you can think about how to make it work on other characteristics. Yeah, the proof is super simple. I'm not done, but so what's going on here? Let's consider this polynomial, right? By the Taylor expansion of this, you can see that you'll get different monomials, like t to the b will show up somewhere, and its coefficient is going to be this guy. If you just stare at it, you'll see. But we know how to extract coefficients, right? we did this by interpolation already. So the coefficient of t to the b in this is the same as coefficient, because it's in the exponent now, I can just like put it as multiplication. And then these are univariates now. They fall apart as products of univariates. It's a little bit of work. Each of this is now TB of Z1. You have to interpolate, and then I have not presented the whole proof, okay? But going from here to here is not very difficult. Yeah. The main take back message of this is that powers of sums can be written as sum of univariates.
The factor is sum of univariates, but they're like SP plus 1.
SP plus 1. There are a little too many of them. Also, it so happens that when you try to extract it out and write this down as TBs, these are highly inhomogeneous thingies here. Yeah, so they are like inhomogeneous polynomials that are univariates that multiply out and then give you that. And the big sum sitting outside is like the linear combinations we take when we do interpolation. Yeah, that we've been doing so far, even in the original interpolation idea. Okay, so why did I tell you all this? It's not just because I like it. Yeah, it also because it proves a theorem I really like. Okay, so that's the final thing I want to tell you. We talked about depth reduction. Yeah, and there were these statements that, oh, you start with a circuit of arbitrary depth, you can go to log n. Not only can you go to log n, you can go to log 4. Not only can you go to log 4, you can go to log 3, depth 3, not log, sorry. Not only can you go to depth 4, you can go to depth 3. Yeah, and if I just look at that final thing, that going from depth 4 to depth 3, yeah, that's nothing but application of these two ideas I told you about, the Riser's formula and the duality trick. Okay? So, now it's a picture proof. You want to start with formula that looks like this, a circuit that looks like this, and go to a circuit that's of smaller depth. In order to do that, we first increase the depth a bit. These are powers. Recall that this is like a monomial. A product of things is like a monomial, right? It's just like, that these are all some polynomials, qi1, qi2, etc. But I can think of them as y1, y2, etc. and expand it out. Every monomial can be written down as sums of powers of sums, we saw. Okay? So I just do that in place. So every product gate sort of gets rewritten as sums of powers of sums in both the places. Okay? This increases the depth, this increases the size, but it becomes a circuit that looks a little bit like this now. All the sums you can collapse together, doesn't matter, everywhere. So you get like sums of powers of sums of powers of sums. Yeah, we went from depth, we want to go to depth 3, but we first went to depth 5. But now you have this, that you have these powers of sums of powers. But we know how to handle powers of sums by this duality trick. So we'll just put the powers inside, like z1 to the a1, zs to the a, z1 to the a, zs to the a, to the power b, and then because these are univariates, I can comfortably, willy-nilly just push the powers in further, and voila. Right? You get powers of sums of powers replaced by sums of powers of univariates. Very pretty. Yeah? And that's a sigma by sigma circuit. Of course, you have to now argue that it's the correct size and so on, but I leave that as an exercise. Yeah? Beautiful paper. So this paper, certainly one of my favorites. And I kind of managed to present most of the ideas. So now we are close to finishing. So just some summary and closing remarks. So what did we see in this whole tutorial of 6 hours? We went through some structural results like depth reduction, homogenization, set multilinearization. We observed that structure helps lower bounds. So we actually saw an example of this as well. We went through the proof of the lower bound for sigma pi sigma circuits at least, which is kind of like the best lower bounds we know today. And in today's session, this was in the second session, and in today's session we kind of saw this connection between lower bounds and PIT. And all along, I have tried to keep this consistent that in my slides, wherever there's like a green box, it's an open question. So you can just like go through the green boxes and see if something catches your fancy. There's a Google Drive link I shared with you. I'll put today's slides also on that. I have added 2 very beautiful surveys that, I would like to say, like this is like a little bit of a brag for algebraic complexity here, which is that many areas do not have well-written surveys for students to start with, okay? But algebraic complexity is not such an area. You have 2 really excellent well-written surveys for this area. So as a student, it's a very nice area to get started with because you have this one place where you see most of the results listed out. Okay, so that's very nice in my view. Barrier to entry is as low as it can be because of this. Of course, there are complexities coming from the material itself. But you don't have to scramble around looking for where should I look for this or where should I look for that. There are these go-to places where you can find most of the stuff. And the amazing thing about this survey is also that it's on Git. So if you read a paper in algebraic complexity and you want to summarize it, you can push your Git update there. And then everybody can see it. So it's a survey being primarily maintained by Ramprasad Saptarshi, but there are contributors to that survey, and it's very nicely done in my view. Okay, and then I actually recently gave a talk at CCC about like a survey talk there, and that has a lot of open questions that I tried to go over. So I'll post those slides as well, and you can take a look at it if you like. And then things I did not cover in this, and there were quite a few. There are connections to proof complexity. I mentioned this, but I did not quite talk about it at all. We didn't have the time. There are many follow-up results after this bounded depth lower bound, which I couldn't talk about, but they are in my CCC survey, so you could take a look at that. Many other results in the area that I'm excited about, but I just followed a theme, and because they were not in the theme, I did not present them. There are barrier results to lower bounds in the area to say that beyond this point we cannot prove lower bounds. I know very little about them, so I left them out, but you can look it up. And there is a whole area in algebraic complexity called reconstruction, and I did not talk about that at all. Again, I know very little about it. And that's it. And if you still have a little bit of patience, so far, I was planning to ask this in the beginning, but so you know what to do, right? Just go to menti.com, and then you can go to put the code 55834611. You can also tell me, but I'll have this with me later then. If you also add it there. Implications, definitions, low bounds, great. open problems. Great. Low bounds, okay, that's enough. I think this is like a word cloud, so if more people say the same thing, it that's a full job. Tricks, yes. Relation, yeah. What would I do? It's hard tricks. Oh, it's hard and tricks, okay. It's hard in a nice way, or it's like hard, I'm not going to do it ever again? Okay, we have quite a few responses. So yeah, thank you so much for sitting through this.
Yeah, so let's thank Nutan again for all the incredible lectures for us.